Hello everybody. I didn't post yesterday's lesson because I needed to wait until we had a finished product. Yesterday, Thursday, the 30th of January, for the whole class period, my students started out with a weird looking piece of graph paper that has 27 dots that I pre-graphed right here like that. Okay. And then what they had to do with it, it was on a blue background. They had to take this information on 27 important stars. There they are, 27 of them. And I'll have the picture of this document, hard copy, linked in Google Classroom. They had to take these 27 stars, and they're just listed in alphabetical order. These are 27 stars that I picked. Okay. And if you look, like star number 1, Aldebaran, is an orange star. And all they had to do on the graph was glue an orange dot on star number 1, which is right here. Okay. And, star number 2, Algol, is white. And that one's over here. Okay. And it seemed random because the list is by alphabetical order. But what happened was, and it took them about more than half an hour, when everybody was done, they had this. Okay. And during class, I made them, as they glued each dot down on top of the number, they had to write the label of that star's name right next to it, because they wouldn't know which ones were which, because people aren't going to have this list on them. And the reason for that is these numbers are just bogus. This list of 27, this is the only list in the world where these stars are on there in that order. Okay. I'm the one that picked these stars. So what you're looking at here is a pretty copy. It's nice and clean of the 27 dots. But now you're like, okay, but what is it? So what this is a graph. It's called the HR diagram. Okay, it's not a map. It is not a map. It is not a map. It cannot be used as a map. It's a personality chart. And it shows you stars based on comparing their temperature this way and their brightness, their true brightness, up and down this way. Okay? Now, that's what we did yesterday. They got a bunch of gluing done, and then all 27 dots were named. Now, they came back to class today on Friday, 31st, and I told them, now I'm going to show you why that matters. Okay? All right, so I'm going to put this phone on a stand. Try to make it so you can still see it. Okay? Now, remember, you're seeing a cleaner version because it doesn't have all the names on it. Okay? I'll show you a version later where the names are done. Okay, so here's what I had people do today. I told them these are temperatures. To a human, all these temperatures are hot. If you look at these degrees, this is in Celsius up here. Okay. But for a star, these are fairly cool temperatures. Okay. 3,000 degrees and so on over here. Okay. If you watched any video of the terrible fires in California, when those winds were whipping, those temperatures got hot enough to melt cars. Not burn them, melt them. Okay, so that's kind of temperatures that might have been happening over here. But as you go this way, the temperatures get hotter and hotter and hotter. These are like welding temperatures and lightning temperatures over here. 20,000 degrees Celsius is incredibly hot, white hot. Okay, all right. So I had the students add the word hot on this end. Okay, now the people that made this chart were curious about something. They didn't know the answer. They're going to make a discovery here. They were wondering if stars got to randomly pick their temperatures and their brightnesses. Here's the big question. Is a star's temperature related to its brightness, or are they unrelated? Do stars randomly get to pick a brightness and a temperature? When they did this graph, they did not know the answer. And this graph took years of work by teams of people to find out the answer. They didn't do 27 stars. They did hundreds and hundreds and hundreds of stars. Okay, now I'm going to turn the page sideways like this. These are the true brightnesses of the stars. I hope this shows up in the video. And I had the students add bright on this corner and dim on this corner. Okay, so we're going to compare, this graph is going to compare temperature, hot on this end, cool on this end, and true brightness. We'll talk about what that means later. Bright on this top and dim toward the bottom. Okay, now these two teams independently, this is around 1900. Okay, the HR diagram was quote unquote discovered, released in 1911. That's before the Titanic, right before World War I. Okay, and here's the shape that results. Okay, this is not connect the dots. Okay, this is the bright star Spica. I'm going to draw the shape without any of the pesky star names getting in the way. A shape showed up on the graph like this. I'm going to be quiet and draw so I don't screw up here. Let me explain what that means. Hopefully you can see that whole thing. I'll move it over so you can see it. That swoosh. Now here's the important thing to know. If you make a graph and a shape shows up, you've just made a discovery. You may not be smart enough to know what it is, but you've made a discovery. A shape is the opposite of randomness. There's something going on here. What it tells you is there's a relationship between a star's temperature and brightness. They don't get to pick randomly. Okay? Randomness would be the opposite of a discovery. Randomness would have been stars all over crazy with zero shape showing up. It gets better than that. This isn't the only shape that showed up. There was a population of stars like this and a population of stars like this. Here's what I have to stress again and again and again. This is not a map. It's a personality chart. These three stars are not near each other in the sky, but they're very similar in temperature and brightness. These two stars are very similar to each other in temperature and brightness. They are not near each other. In fact, they're on opposite sides of the sky. Okay? If you have two stars near each other on this chart, it means they're similar. Now, notice there's one little star down here by itself. That's Sirius B. And there was a population of stars about like that shape. Okay? So let me emphasize again. They didn't do this with little dots glued on a piece of paper. These are probably graduate assistants, research assistants using big pieces of graph paper and old school pencils. And they're dotting these stars after they found out their temperatures, which you can do by running the light through a prism. But the hard part is finding out how bright a star really is. Its true brightness, which I'm going to tell you about later. When they did this, hundreds and hundreds of stars, this was practically solid with dots. And there was a smudge of a smaller group of stars up here, and a smaller group of stars up here, and a smaller group of stars down here. Now notice, not all stars are on this. There's a few that are just odd. Okay? Remember, this is not a map. All right. This began to be called the main sequence. These are normal, boring stars, the kind of star you'd want to live by. That's the sun right there. They did not rig this to make the sun be in the middle of the chart. The sun is middle of the middle of the middle, boring and safe. These stars live short, violent lives. You would not be able to live by one. The radiation levels would make life impossible. This group of stars, small white stars, very hot, very small, are called white dwarfs. I gave you just the most famous one of all. Sirius B is there. Okay, these stars, oddly named, when you look at this, the orange dots, these are called red giants. You're like, yep, why not orange giants? And I'm starting to write the wrong word there. Giants. Okay, they're redder than they used to be. They're yellow. As they cooled off and they aged, you put a little bit of red with your yellow, they'll get orange. And these are more red. These are called red supergiants. Red supergiants. Okay? Now, what this lets us know is what a star is doing in its life at the moment, what kind of star it's like, and its future. Stars right here are minding their own business. They're in the middle of their lives. They're doing fine. These stars are retirees. They're cooling off. Okay? They're kicking back. These stars are about ready to die. Okay? This star right here is Betelgeuse. It's a star, if you look up Betelgeuse on the internet, there's all kinds of speculation of when it's going to blow up. It'll be spectacular. Everybody in the world will see it, day or night. You'll be able to see Betelgeuse when it blows up. It's going to be bright. Anyway, now, this is the first stuff we did today. Now I'm going to show you something a little bit weird, because I have to talk to you about how much work it was to determine a star's true brightness. All right, I'm going to show you a weird video clip. This is on YouTube. It's from the 1992 movie Wayne's World. It might be Wayne's World or Wayne's World 2. I don't remember which. It's the main character goofing around with his girlfriend. And this is going to be a weird scene. I know that. I'm going to go hit play. All right, here we go. I'm just showing you on my screen. Okay. They have their clothes on. They're messing around in bed. There's nothing going on here inappropriate. Okay, watch this.
Camera 1, camera 2, camera 1, camera 2, camera 1, camera 2, camera 1, camera 2.
Now, what was that all about? Was she moving around? No, she wasn't moving a bit. It looks like she was moving because he kept changing his which eye he was looking at. Okay? Now, these are the notes that I gave everybody today after we drew in the groups. How do you find out a star's true brightness? That's tricky. All right. These are going to be the notes. I'll just put these over here to the side, and here we go. Give me a second. Sorry about, my nose is plugged up. The HR diagram. All right. By the way, here's the finished version with all the star names on it. That's what everybody has in their binders. Okay. You can see the same labeling. All right. I just did it on blue paper because it looks nicer. Okay. This is a very important tool for us during the astronomy unit. Okay. All right. I would argue the HR diagram is the 5th most important tool we have in astronomy. Eyes being number 1, camera number 2. Let me see. Telescope. You could argue back and forth on whether telescopes are more important than cameras. Okay. So eyes, telescopes, cameras, spectrographs, where you run light through the prism, and number 5. The HR diagram, for letting us be able to study what age a star is and how much longer it's going to live, what part of its life it's in. All right, here, the HR diagram is from 1911. It was made by 2 teams working independently. Hopefully this is showing up. I'll move it over. 2 teams working independently. Now, the H stands for Hertzsprung. That's the astronomer's name, who is the head of his team. He's in Austria. And the R, working separately, I don't know if they knew I don't know that they knew the other team even existed. Russell's team is from the U.S. Both teams had the same question, and both teams did this work that took years, not knowing if there was going to be an answer. If there was no relationship between temperature and brightness, true brightness, they would have found this out because the graph would have been nothing, and they would have wasted a lot of time and money. But they got famous because this is the key to the lives and deaths of stars. Two teams working independently, okay? They compared the temps and true brightnesses of hundreds or thousands, I'm going to say thousands, of thousands of stars. I'll give you a little sketch of what we made on the other side. Here's what showed up. That's amazing. A graph that produces a shape is telling you something, and then it's your job to figure out what that is. And they figured out, oh, there's only certain temperatures and brightnesses that go together. Stars don't randomly get to pick. All right. Now, how do you find out the temperature? Temperature can be measured, this is going to be very shorthand, by measuring the light of the star through a prism and see how much the light patterns are shifted. So I'm just going to write temps can be measured with the prism. The light shining through a prism and then coming out the other side. Okay? That's fairly straightforward. That doesn't take very long. You can do that in one night. But finding out the true brightnesses of these things is something else. And then the Wayne's World video clip that I just showed you, camera 1, camera 2, is where I'm headed with that. The true brightness is tougher and time consuming. Here's what they had to do. They had to figure out how far away that star was from the Earth, because that's going to determine its brightness. A bright object right in your face is going to seem dimmer and dimmer and dimmer as it gets away from you, even though it did not change how much light it was putting out. If it's farther and farther and farther away from you, it looks dimmer. Okay? We say that the brightest star in our sky is the sun, because it's right next door. But if you'd put it way out where the other stars are, you'd lose it, because it's in the middle of the pack for its true brightness. This is the sun right here. All right, so how do you find out the true brightness? Okay, when Wayne was looking at his girlfriend, camera 1, camera 2, camera 1, camera 2, it looked like she was moving. She wasn't moving. He just was blinking, closing one eye and the other eye, changing his perspective by about that much, the distance between his two eyes. The shift that it looked like was happening, when it looked like she was going from the left to the right to the left to the right, was being caused by his changing in perspective, his change of perspective. Okay, now here's the trick. This is very clever. Here's the sun. Here's the earth. This is 93 million miles. In 6 months, the Earth is going to be over here. And this is not a very good drawing, but that's also 93 million miles. Pretty close, okay? It's not a perfect circle, but it's really close. So here's the thing. When you look at some object with your right eye and then your left eye and then your right eye and then your left eye, if it's close enough, it will seem to jump back and forth. You can do this with a finger held out in front of your face. Camera 1, camera 2, camera 1, camera 2. All right. You know that the finger isn't moving, and you know it's because you're blinking one eye and then the other. The astronomers did this. They took pictures of the night sky in the evening of a patch of sky, took a nice clear picture. Then they waited 6 months till the Earth was on the other side of the sun. And then they took another picture of the same chunk of sky. It'd be in the morning now, but it's the same picture. But they've moved 186 million miles. If you put the two pictures together to line them up, some of the stars will shift a little bit. And they didn't move. We moved. And the more it shifted, the closer the star was. They figured out a way to measure those tiny shifts in those stars. If a star didn't shift at all in between the two pictures, it was too far away for them to know how far away it was. If it shifted a little bit, they knew it was pretty far away. If it shifted a lot, they knew that star was close to us. Isn't that clever? So, here's the last thing. We're almost done. I got to look at the time. I'm at 20 minutes already. Better hurry up. All right. So, there's two kinds of brightness. Apparent magnitude, which is how bright something looks. How bright something looks. But that's affected by distance. We think the sun's incredibly bright because it's so close to us, but that's just because it's so close, affected by distance. Here's what true brightness is. Absolute magnitude. This is how bright something really is. And the way you do that is how bright something really is. I have to slow down so I write this. How bright something really is. And that's as viewed from a standard distance. So the scientists picked a distance that how bright would this star look from this distance, and they did that with all the stars that they knew the distances of, so they could compare them fairly, as viewed from a standard distance. That is what absolute magnitude is. Okay? So they used absolute magnitude here, the true brightness of the star and the star's surface temps, and that gave them this shape. All right, that's how far we got in 2 days, constructing the diagram and then labeling it and talking about how you find out where a star fits on this personality chart. I'm going to put this on YouTube and put it on Google Classroom. Email me if you have any questions.